Okay, we hear this phrase all the time. AI learns from data. It sounds so simple, right? Almost like magic. But what is really going on inside the machine? How does a piece of code go from just looking at raw information to making these incredibly smart predictions? Well, today we're going to pull back that curtain and demystify the whole process step by step. So this is the big question we're tackling. We are going to peel back the layers and look at the actual mechanics of what we call machine learning. Because, it's not magic at all. It's actually a fascinating, totally logical process of trial and error. It just happens at a speed and a scale that is almost impossible for us to wrap our heads around. So here's how we're going to break it down. We'll start with the big picture, the AI project lifecycle. Then we'll zoom in on getting the data ready, the learning loop itself, how the model actually corrects its own mistakes, and finally, how this all works at a massive scale. All right, first things first. Training an AI model isn't something you just do. It's not a single action. It's actually just one critical step in a much larger, very structured process that professionals have to follow to build something that actually works in the real world. And the key thing to get here is that this whole process isn't a straight line. It's a loop. It's continuous. You don't just build a model and, walk away. You have to deploy it, you monitor how it's doing, and that feedback often sends you right back to the beginning to get more data or to retrain the whole thing. It's a really disciplined engineering cycle. And these are the main stages. See, you can't just throw a bunch of data at a computer and hope for the best. You have to really understand the problem you're trying to solve, collect the right data, clean it all up, and so on. Now, for the rest of our time today, we're going to zoom way in on just one of these steps. Number 4, train model. But it's so important to remember it never, ever happens in a vacuum. Okay, so before any real learning can happen, you have to prepare the ingredients. And in machine learning, the only ingredient that really matters is data. The problem is raw data is almost never ready to be used right out of the box. This quote right here just says it all. Real-world data is messy. It's got missing values, it's got typos, all sorts of inconsistencies. I mean, think about a spreadsheet where someone's age is listed as -2003 or their income is in a totally different currency. So a huge amount of work goes into cleaning and standardizing all this data just to make it usable for a machine. Now here's a crucial point. You don't use all of your nice, clean data for the learning part. You split it. Most of it becomes your training data. That's like the textbook the model gets to study from. But you hold back a chunk of it, and that's your test data. This acts like a final exam, with questions the model has never seen before, to check if it actually learned the concepts or if it just memorized the answers from the textbook. So our data is prepped and ready to go. Now we can finally look at the heart of the learning process itself. How does a model go from being completely wrong to being right? Well, it's not one giant leap. It's a continuous loop of tiny, tiny improvements. The main algorithm that powers this loop is usually something called gradient descent. And honestly, the best way to think about it is like this. Imagine the model's error rate is a giant, hilly landscape. The model is like a ball you place somewhere on that landscape, and its only goal is to find the absolute lowest point, the valley, where the error is at a minimum. Gradient descent is just the process of that ball taking small, smart steps downhill until it literally can't go any lower. So this is what it looks like at the very beginning. When you start training, the model's internal settings are basically random. It makes a guess, and as you can see, that guess is way off from the real data. The error, which we call loss, is super high. We're at the very top of that hill I was talking about. But then, after thousands of iterations of that rolling downhill process, look what happens. The model has adjusted itself over and over and over again, and its prediction line is getting much closer to the actual data points. The error has dropped a lot. The ball is getting way closer to the bottom. And finally, we get here. This is a point we call convergence. The loss curve flattens out because, well, the model has found the bottom of the valley. It has figured out the best possible settings to make the error as low as it can be on the training data. At this point, you could say it has learned the pattern. Okay, so we know the model improves by iterating, but how, mechanically, does it make even a single one of those corrections? Let's zoom in as far as we can and look at just one loop in this process. So let's get really concrete for a second. In this example, for a certain input, the model was supposed to output 0.01. Instead, it guessed 0.751. I mean, that's a pretty big error, right? The whole learning process starts by calculating this difference, the gap between the guess and the right answer. This first step is what we call the forward pass. The input data literally flows forward through the network, and based on its current internal settings, you can think of them as thousands of tiny little knobs called weights and biases, it calculates a prediction. In our case, that was the wrong guess of 0.751. Now, this is the really clever part. It's called the backwards pass or backpropagation. The network takes the error it just calculated, that big gap between 0.751 and zero point zero 0.01, and it works backward through the entire network. It figures out how much each of those thousands of tiny knobs contributed to the mistake, and it nudges each one just a tiny bit in a direction that would have made the error smaller. And here's the result of that one single correction. The total error for the network went from about 0.298 down to 0.291. It's not a huge drop, is it? But this is the fundamental atom of learning. It's one tiny, perfectly calculated step in the right direction. Now, that one tiny adjustment might not seem all that impressive by itself, but what happens when you repeat that simple process millions or even billions of times? Let's zoom back out. Remember our example? The one where the error started up at 0.298? Well, after repeating that simple correction process 10,000 times, the total error plummets to this tiny little number. The model's guesses are now almost exactly the same as the target answers. That is the power of iteration. This right here is the core principle behind all of modern AI. When you hear about a large language model being trained, it's doing this exact same thing. Each correction is minuscule, but when you repeat it across billions and billions of examples, those tiny adjustments accumulate into a model that can write poetry, generate code, or answer incredibly complex questions. So when you strip away all the complexity, all the hype, what you're left with is this surprisingly simple and, well, elegant engine. The incredible power of modern AI is built on this very basic loop. Make a guess, measure how wrong you were, and make a tiny correction so you're a little less wrong next time. So let's just quickly recap the key things to take away. First, AI training isn't magic. It's a structured engineering lifecycle. Second, you have to clean and prep your data. It's non-negotiable. Third, the core of learning is this iterative loop of minimizing error, a process called gradient descent. Fourth, those tiny corrections are made using a technique called backpropagation. And finally, it's the absolutely massive scale of this simple loop that creates the powerful AI models we see today. And that leaves us with one final thought to chew on. We've seen that at its very core, this kind of learning is a mathematical process of optimization. It's a really sophisticated loop of guessing and correcting. So if that's all it is, what does that imply about the nature of intelligence itself? And what are the true limits of what a system like this can ever really truly know or understand?